One reason. Yesterday. Yes, I did yesterday. I booked like. Yeah. Oh, no. Oh, it's okay. I need it to me. No, but I also like, I don't want to. Almost like it. No, like if you have regular M&Ms, I would feel like, oh, I was not using it. They were like oil, like something in there. Like in the shells. I think actual peanuts like in the shell or something in there. It's still good. Oil and salt water in the shell. And it's all covered. I'm not going out with the girls this weekend, so like maybe I'll.
Oh, yeah. Yeah, but this part, like if they're like that.
Can't sit on the upset that everyone's gone because finally we can find this.
That's true. That's true. Until it's exam day and everyone comes and then they're all like,
I've been here. Give us some space. Exam is next week. I'm assuming.
no, week after next.
Okay.
Yeah, because we're gonna be doing a plus up until end of next week.
Yeah.
And then exam will be
I don't like.
week 7, which I know is a popular week for exams, but yeah, that's just how it's done.
There you go.
So halfway through.
Pretty much, yeah.
So then midterm 2 will be pretty close to final.
The after midterm 1, we accelerated a little bit, so midterm 2 will be week 13. And then we'll have kind of one more unit after midterm 2. Which lasts like 2.5 weeks, and then we'll take
It's just like chill.
That's not too bad. I have an exam next week too, so I'm okay.
Okay. Yeah, 6, 7, 8. I know that's when midterm 2 is.
If he doesn't like you, or if you don't like him, it's like. That there. No, it's literally like there's no question.
I know. But honestly, I would have that.
We would just start with you.
Like,
during.
you
And he's not doing those like.
You know,
Well, they're not.
they go. I know.
It was a great, it was such a great meeting. So you think it's so much more. We take it forward. And I was very interested. Oh my God, I really read it. Now it's okay. Yeah.
That's why I said.
It's the one time like you like miss lecture and class and like how those like he cares if he's like that doesn't get too much. Sure. And like there's like a lot of yeah, but like you go to a you're not supposed to miss like yes, and so
Yeah, yeah, I get that. So. But he's like, it's usually different. He's doing it's like, we're going to this. I guess like everyone.
go to my rules, whatever you like, so we're getting I'm really excited. It's like
Like that's a little. Everything on our
yeah.
All right, it's 4 o'clock. Let's go and get started. All right, good afternoon, everyone. How's everyone doing today?
Spectacular.
Good, good. Everyone keeping warm. It is freezing outside right now. I do not do well in the cold. So yeah, it's when I go home, my heater's cranked up to 1,000,000. But when I'm here, I'm just dying of frost while I'm here. Okay. So plan for today is we're going to continue on with our lecture notes on Laplace transforms. We're almost done with part 1, Laplace transforms. So this part 1 portion is really we just kind of get to the point where we can solve differential equations. And then we're going to start part 2 on Thursday, where you'll see that we're going to start to do some more specialized forcing functions. Right? Everything okay, guys? Right. So that's the plan for today. One announcement: homework 3 is posted, so homework 3 is due next Friday. It is a little bit of a tight squeeze, just because I'm not planning to finish up all the Laplace stuff until next Thursday. But you should be able to do everything in the homework up until the very last problem by the end of this week. And then just that last problem is usually not too long. So I would definitely recommend getting started on the homework. After today, you should be able to do, I would say 60–70% of it. And then just the last problem or 2, you can kind of save until next week. So the reason, the homework is due kind of early next Friday, while we're still kind of going over the Laplace stuff, is that our midterm is coming up. So our midterm exam is not next week, but is the week after that. So I want to make sure that homework 3, there's, you guys are able to finish it. I can grade it. I can put the solutions up, so it's all there for you to study before the exam during week 7. Okay.
Tuesday or Thursday?
Thursday. Yeah. So midterms I always have on Thursday, just so it's the last thing of the week. Yeah, so midterm week will be interesting. So on the Tuesday of midterm week, we'll be starting a new topic. That new topic will not be on the midterm. So cutoff for midterm 1 will be next Thursday. So we have basically 4 more lectures to go for the first midterm. And then, we'll start kind of something new, but that stuff's not going to be on the midterm. Okay. So the plan for the midterm is really just this differential equation stuff. So everything we've covered: first order, second order equations, mass spring damper, Laplace transforms. And that's basically gonna be your homework 1, homework 2, homework 3. Okay. We'll talk more about the format of the midterm exam starting next week. But I think I mentioned before that, for the midterm exam, you guys are allowed to bring a cheat sheet. So that's 1 8.5 by 11 sheet of notes. You guys can bring calculator, you guys can bring pencil, paper, no, just pencil, sorry. Pencil, eraser, cheat sheet, and calculator. That's the main things. Okay. But we'll talk more about format, number of questions. We'll kind of go over that next week. Once we're a bit closer. Okay. All right, any questions I can answer before we get started for today? Okay, all right, so let's go ahead and pick up where we left off. And so we were covering Laplace transforms. Okay. Specifically, the whole reason we're getting into Laplace transforms is to give us another way to solve our differential equations. Okay, so we kind of left off right in the middle of doing that. So just to kind of jog your memory, so solving a differential equation with Laplace transforms is essentially a three-step process. Okay. So step one, you're going to be taking the Laplace transform of your entire differential equation. Okay. So if you remember from last time, we learned how to take the Laplace transform of derivative terms. And so that's going to lead to a certain expression. Okay. All right, step two. All right, so after you take the Laplace transform of your ODE, the main thing that you should see is that, we're no longer going to have any derivatives. And so essentially we have just an algebraic expression that we need to solve. So step two is to algebraically solve for the Laplace transform of our solution. Okay. Right. So just like just like when we solve an ODE the classical way, we're after an expression for our solution, y of t. But when you apply Laplace transforms, you don't get y of t directly, you get its Laplace transform y of s. Okay. Right. And then after you solve for y of s, step three is to simply take that y of s and then take its inverse Laplace. Okay. And then that's going to get you your y of t, your solution in the physical domain. Okay. So basically, for any differential equation, you can apply this process, and that applies to all the differential equations we've looked at up to this point as well. Okay. There's only one problem with this, and so in between step two and step three, right? Well, first of all, let's recall kind of how we take the inverse Laplace. So typically, the way we take the inverse Laplace is that we essentially just do pattern matching. And so we look at the structure and the form of our Laplace transform, and we try to match it up with a certain entry in the Laplace transform table. Okay. So as long as our Laplace expression has a form that is in our Laplace table, then we can take its inverse, no problem. Okay. The issue is that, after we do step two, most of the time our expression for our Laplace or our solution is not in a convenient form that we can direct the inverse. And so there's one additional step that you have to do here. And I say that as if it's a small thing, but you're probably going to spend the majority of your time in the problem doing this, which is partial fraction decomposition. Where again, the whole purpose of doing the partial fractions is to simplify your Laplace expression to something that's more easily inversible. Okay. Okay, so that's essentially what we're going to do, and basically for the next 4 classes, we're going to be following this process of take the Laplace term for your ODE, so algebraically solve for your solution, then take its inverse, and then most of the time apply partial fractions along the way. Okay. Okay. So there, we spent quite a bit of time last Thursday talking about partial fractions, but there is actually one more example that I need to do with partial fractions for a somewhat of an edge case that you may see in certain situations. Okay. All right, but before we get to that, are there any questions on just this whole process here? Okay. All right, so let's look at partial fractions one more time. In particular, we're going to look at a situation where we cannot factor the denominator any further. All right, so as always, the best way to kind of illustrate this is with an example. Okay, so with this example, let's look at the following Laplace expressions. We have big F of S is equal to S minus 3 in the numerator, all divided by S cubed plus 3S. Okay. And as always, with this Laplace expression, we are interested in finding its inverse, F of t. Okay. Good. All right, so first thing we're going to do, so that denominator, we're not going to be able to factor too much, but at the very least, we can at least factor out an S from both sides, okay? Or from both terms, excuse me. So on top, we have S minus 3, and on the bottom here, we have S multiplied by S squared plus 3, okay? And so what we're left with here in the denominator is we have an unfactorable quadratic term. Okay? So this we are unable to factor anymore. Okay? And by factor, so if you look at all the previous examples that we did for the partial fractions, we looked at cases where every expression or everything that we kind of partial fraction decomposed into, the S term had a linear exponent. And so in this case, we have S squared. And so this is basically S to the power 2, but we can't factor it in. All right, so luckily, we can still decompose this. Okay. And so let's see what that would look like. And so if we have S minus 3 all over S times S squared plus 3, okay. First thing is that we're going to have one decomposed term that is over S, right? Since we've kind of taken that out. So our first decomposed term is going to be A over S. Okay. And then our second fraction that we're going to add here, its denominator is going to be S squared plus 3. Okay. Since we can't factor that anymore, so we have to have a term that has that entire thing as its denominator. Okay. The only difference is that in the numerator, because our denominator here has a power of 2, that means our numerator has to be 1 power less. Okay? And so in the numerator here, we're going to have BS plus C. Okay? So since denominator has S to power 2, okay. So whenever you're doing partial fraction decomp, right, and you end up with the term in the denominator where, you know, you have s squared or s cubed, s to the fourth, right? You know, you can still decompose that, but you have to make sure that you account for it in the numerator. So the numerator always has one power less than the denominator. Okay. Now, for our purposes, you know, with Laplace, you're never going to see anything beyond s squared. I'm not going to throw an s cubed at you just because that's we don't have an entry in the table for that besides t squared, but you know that one you kind of rarely see. So you know this knowing how s squared in the denominator works is kind of good enough for our purposes. Okay, and you can see that same pattern applies to our first term here. So you know in the denominator for our first expression here, this is s to the power of 1. Okay, whereas in the numerator, right, 1 less than 1 is 0. And so this has s technically to the power of 0. Right? Right, so numerator always 1 power less than the denominator. Okay, but besides that, you know, we follow the exact same partial fraction process. And so let's take this, just like we've done in our previous two examples. Let's multiply both sides by the complete denominator. Okay. And so we do that. We multiply both sides by s times s squared plus 3. That means on the left-hand side, we have s minus 3, because that's going to cancel out with the denominator there. And we have a times s squared plus 3 plus bs plus c multiplied by s. All right, and so from here, you know, it's fairly straightforward. So we basically just have to distribute group-like terms and then use that to solve for a, b, and c. Okay. All right, so first thing, let's distribute. So we have a s squared plus 3a plus b s squared plus cs. Still s minus 3 on the other side of the equation. All right, so now let's group our like terms. So let's group the s squared terms. So we have a plus b multiplied by s squared. Our s terms, we only just have one, which is c. Okay, and then our constant term is just 3a. Okay. Okay, so now from this, we can go ahead and form our system of equations. So let's go ahead and equate the like terms on both sides of the equation. Okay. So first we have s squared. So we don't have any s squared term on the left-hand side, so we can go ahead and set that to 0. Okay. And on the right-hand side, our s squared is a plus b. Okay. For our s terms, and so on the left-hand side, the coefficient for s is 1. Okay. And on the right-hand side, the coefficient for our only s term is c. Okay. So that gives us an equation that we can solve straight up for the value of c. So c has to be equal to 1. And then our constant term, left-hand side, we have a minus 3. And the right-hand side, we have 3a. Okay. All right. All right, so let's go and solve the system. This one's fairly straightforward. So first off, we see that c is equal to 1. Okay. We can see that a is equal to minus 1. Okay. And then if a is minus 1, we go ahead and plug that back into our top equation here. That means b must equal to 1. Okay. Okay. So now plugging these in to our partial fraction decomp that we defined earlier. Okay. We get the following expressions. We have s minus 3 over s times s squared plus 3 is equal to minus 1 over s, that's our value of a, plus s plus 1 divided by s squared plus 3. All right, so now that we've decomposed this, we are ready to inverse because these are terms that are much easier to inverse, or at least we can inverse this with the table much more easily. Okay. All right, so inverse of this, and so we have -1 over s. This is the Laplace transform of -1. All right. Next, we're going to break this up into two terms, right? So we have an s over s squared plus 3 plus 1 over s squared plus 3. Okay. All right, so s over s squared plus 3, this one is fairly simple. So this is our cosine, right? So whenever we have s squared plus a number on the denominator, that's essentially our calling card for cosine. Okay? The only thing that's weird here is that our frequency is actually square root of 3, right? Because remember, you have cosine omega t, right? You take its Laplace transform. It's s over s squared plus omega squared. Okay. So don't forget that. So don't forget that, for cosine and sine, you take the square root of that omega. Okay. Or you take the square root of omega squared, excuse me. And so this right here is the Laplace transform of cosine. And our frequency is square root of 3, which is root 3 times t. And then our last term there, which is just 1 over s squared plus 3, that looks like our sine, right? Because if we go back to our table, our Laplace transform of a sine is omega over s squared plus omega squared. Okay. Okay. So the only thing that's challenging here is that, remember for sine, we do have to get our frequency up in the numerator. So we don't have that right now because we have 1 over s squared plus 3, but we can do our usual trick where we just kind of multiply by 1. Okay. And so we multiply this entire thing by root 3 over root 3. Okay. We can then move this root 3 up into the numerator. And so that gives us plus 1 over root 3, Laplace transform of root 3 over s squared plus 3. Oh, excuse me. Laplace transform of sine root 3 of t. All right, so now that we have a matching entry from the table for every one of our terms, you can just go ahead and just apply those. And so finally, our f of t in this case is -1 plus cosine of root 3 times t plus 1 over root 3 sine of root 3 times t. All right, any questions on this example here? How we got these results? Okay, good. All right, so now that's it with partial fractions, and so we're now ready to solve differential equations. But I did want to kind of summarize these 3 cases that we went over for partial fractions, because these are the 3 most common cases that you'll see. Okay. Okay. So I have this table. So this table is provided to you. So in the so for the exam, I will be providing you a sheet which has all the table in Laplace transform. It'll have this table of partial fractions as well. So that's something that you don't have to write yourself on your cheat sheet, but I'll provide that for you. Okay. Okay. And so all right, so the table looks like this. And so there is a column for the denominator. Okay, so basically what you see there. And on the right-hand side of this table, we'll show you kind of the form of the partial fraction decomp. Okay. Okay. So first case here, this is the most simple case. So this is when you have a linear expression for S. Okay? So if we have AS plus B in the denominator, then the way that this decomposes is that we have an A over AS plus B. Okay. Pretty simple. So, we basically just break it apart and then we kind of put it in its own term, separate from everything else. Okay. Next, we have the repeated root. So these are cases when we have AS plus B raised to some power n in the denominator. Okay. All right, and remember the way that we did this was kind of a special case where we kind of expanded our denominator into all the different possible exponents that lead up to the n, right? And so the way this partial fraction decomp goes is that we have an A1 over AS plus B plus A2 over AS plus B quantity squared. Okay. And you keep adding terms up until you get to the point of the AS plus B raised to the n power. So that was kind of the last example that we did on Thursday, right? So when you have basically a repeated root, the same term that's raised to some power, then you break that up into all the different terms and then just kind of add them together. Okay. And then finally, the one that we went over today, which is an unfactorable quadratic. So this would be AS squared plus BS plus C, right? And the way we factor this is that we put a linear function in the numerator. So that's partial fraction decomp is AS plus B all over AS squared plus BS plus C. Okay. So those are all three cases for partial fractions that you'll see basically in every situation for this class. All right, any questions on this? Okay. All right, so the last thing to do and kind of my plan for the rest of class today is just to do examples. And so the thing with Laplace, just like most mathematical techniques, is that you just kind of get better with practice. You can look at the theory, you can look at the proofs all you want, but at the end of the day, it's math is kind of a muscle that you have to practice. So let's do a few examples today. Okay, so I believe we started this example last time. So let's just go ahead and kind of finish it. So we have d squared y dt squared minus y is equal to t. And we have our initial conditions. Y of 0 is equal to 1. And then dy dt at t is equal to 0 is also equal to 1. Okay. All right, and so for this one, we want to solve for the solution y of t. And we're going to do that using a Laplace transform. Okay. All right, so fairly simple example to start with. All right, so we're given a differential equation here. This is a non-homogeneous equation just because we have a non-zero right-hand side. We're given our initial condition. So we have an initial condition for the solution itself, as well as this derivative. So this is kind of prime opportunity to use Laplace transforms. Okay. All right, so let's go ahead and do our three-step process. All right, so step one, let's take the Laplace transform of the entire ODE. All right, so we have three terms here. So let's go ahead and do that. So we're going to take Laplace transform of d squared y dt squared minus y is equal to t. Okay. All All right, so remember Laplace is a linear operator, so that means we can take the Laplace transform of this entire equation and just apply it individually to each of the terms. So it's going to be Laplace transform of d squared y dt squared minus Laplace transform of y is equal to Laplace transform of t. Okay. All right. So remember, we don't know the value of y yet. That's kind of our unknown solution that we want to solve for. And so when we take Laplace transforms involving y, we just leave it as this generic kind of y of s. Okay, so let's go ahead and complete this. So first thing is that we have our Laplace transform of our second derivative. Okay. So this is s squared minus big Y of s, okay, minus little s times little y of 0. That's one of our initial conditions, minus dy dt at t is equal to 0. This is subtracted by the Laplace transform of just y, and so this is big Y of s. And then we have our forcing term, which is the Laplace transform of just t, and so Laplace transform of that is 1 over s squared. All right. Let's go ahead and plug in our initial conditions, just because we can do that right now. So from our initial conditions, we know that y of 0, let me just kind of scroll up a bit. Okay. Y of 0 is equal to 1. And we also have information on the initial value of the derivative of the solution, which is also 1. All right, so let's go ahead and plug those in, and let's go ahead and move them algebraically to the right-hand side. Okay, so we're on to step 2. All right, so after we've applied Laplace transform to the entire equation, we've plugged in initial conditions. Step 2 is to basically solve for y of s algebraically. Okay, so to do that, we're going to take everything that's not s and we're going to move it to the right-hand side. Okay, so that means both of our initial conditions. And on the left-hand side, all we're left with is big Y of s multiplied by s squared minus 1 is equal to s plus 1 over s squared. All right, and then last thing we're going to do here is we're going to divide both sides by s squared minus 1. So that'll isolate y of s for us. Okay. Okay. All right, so we do that, we get big Y of s is equal to s plus 1 all over s squared minus 1. Okay, so I'm going to group those two terms together, and you'll see why, or maybe you already see. Okay, and then our other expression here is 1 over s squared multiplied by s squared minus 1. Okay, so let me simplify that first term first, because we know that s squared minus 1, this is equal to s plus 1 quantity multiplied by s minus 1. Okay. So we basically just have the form a squared minus b squared. So we just kind of utilize that. So this is s plus 1 divided by s plus 1 multiplied by s minus 1. So the s plus 1s are obviously going to cancel out. And so all we're left with that first term is 1 over s minus 1, which is very, very easy to deal with. right? That's just a simple kind of, one step inverse. There's no partial fractions we have to do. It's basically just an exponential function. Okay. All right, so then now we have our other fraction term, which is not going to be as simple. Okay. So in order to invert this 1 over s squared multiplied by s squared minus 1, we do need to do partial fractions on this to simplify it into a form that we can actually use. Okay. All right, so let's go ahead and set up our partial fraction decomp. So we have kind of actually the combination of two separate scenarios here. Or you can have it be a combination of a different two scenarios. And so it's kind of however you want to slice it. Okay. You end up with the same thing. Okay, so on the left-hand side, we have our fraction that we want to decompose. So it's 1 over s squared multiplied by s squared minus 1. Okay, first thing we notice is that we have essentially a repeated root. So s appears by itself in the denominator with a factor of 2. Okay. So remember, we can factor this, but we have to account for every power of s up until that point. Okay. So this is going to be a over s plus b over s squared. So both of those first two terms there come from the s squared in our starting fraction. Okay, and the other part, so I'm gonna treat this as an unfactorable polynomial, even though I know you can factor. We literally just did it right above here. But just for kind of illustrations purposes, let's do this in terms of an unfactorable function. Okay. And so this is going to be denominator s squared minus 1. And then in the numerator, we have to account for every power of x and leading up to second power. So this is plus cs plus d. Okay. Another way that you could have done that is you could have broken up that s squared minus 1 into s plus 1, s minus 1, and then that gives you two separate terms in your decomp. So that's perfectly valid as well. Okay. So from here, let's go ahead and solve. So first thing is we need to multiply by our common denominator. Okay. Which in this case is the product of s squared multiplied by s squared minus 1. Okay, so let's go ahead and do that. So left-hand side, after we canceled that denominator, all we're left with is just 1. And then right-hand side, we have a multiplied by s times s squared minus 1, okay, plus b multiplied by s squared minus 1, plus c s plus d multiplied by the remnants here, which is just s squared. Okay. All right, so let's go ahead and distribute combined like terms just like we have done before. All right, so after we distribute, we get as cubed minus as plus bs squared minus b plus cs cubed plus ds squared. Okay. All right, so all I did was I just took all of our multiplications and just multiplied it all out. Okay. Okay, so let's go ahead and group the like terms. And so first we have our s squared terms. And so for s squared, we have a plus b. Oh, excuse me, this is this s cubed. I knew something was wrong. Yeah, so a plus c, thank you. Okay. Right. And so remember, one thing I like to do when you're kind of working with these long expressions and you're kind of copying things down, you're combining like terms, I like to just kind of cross it off, right? Just so I don't kind of double count it, right? So we've already kind of used those, so let's just kind of get rid of it. All right, next we have our s squared term. So s squared is just, we have a b plus a d. This is multiplied by s squared. Then we have our linear term. So our linear term is just minus a times s. Okay. And then our constant term here is just a minus b. Okay, so everyone is accounted for. We are now ready to solve this system for 4 constants, a, b, c, and d. Okay. So let's form our system of equations just like we usually do. So we have an s cubed, s squared, s, and constant. Okay. So our s cubed equation, on the left-hand side of this expression here, we don't have any s cubed. And so that we have a 0. And then on the right-hand side, we have a plus c. For s squared, we also don't have any s squared terms on the left-hand side, so that's 0. And this is going to be equal to the s squared term on the right-hand side, which is a b plus a d. All right, next we have the linear term. So for the linear term is just s. Left-hand side, we don't have any linear terms, so left-hand side is also going to be 0. And then right-hand side, we have just one s term, which is a minus a. Okay. Sorry, I realized I put an s on the right, but I forgot about it. We'll just go over it. That's better. Okay, and then finally we have our constant term. So we do have a constant term on our left-hand side. So our constant term on the left is a 1. Okay? And this is equal to the constant term on the right-hand side, which is just minus b. All right, so now we have a system of equations here that we can solve for a, b, c, and d, right? So 4 equations, 4 unknowns, usually is a little bit intimidating, but a lot of times you'll get systems like this where, a couple answers just kind of come off the page very easily, right? So first thing we can see is that the only admissible value for a is 0. Right, so that's the only value of a that can be there to satisfy that equation. And we also have the value of b straight up, excuse me. So b has to equal to minus 1. All right, and then we can plug these into our equation above to kind of give us, what's left here. And so we have a plus c is equal to 0. So that means c is also equal to 0, since a is equal to 0. Okay. And then d, if b is minus 1, that means d must be positive 1 in order to satisfy this equation. Okay. So let's go ahead and write out that partial fraction decomp. Okay. So first thing is we have, we had our problem here, right? So we have y of s. Well, let's just go off the fraction first. We have 1 over s squared times s squared minus 1. Okay. Is equal to, we have a minus b over s squared. So that is a minus 1 over s squared. Okay. Plus d is equal to 1. And so that means we have 1 over s squared minus 1. Okay, good. So now these two terms here are very easily invertible. Okay, so let's actually bring this together and add it to y of s. So y of s in this case is equal to, we still have our first term, right? So from our first expression here for y of s, don't forget this, right? So first thing we had was our 1 over s minus 1. So y of s here is 1 over s minus 1 over s squared plus 1 over s squared minus 1. Okay. All right, so after all that, we end up with this expression here. And the good news is that everything here, we can invert it fairly easily. Okay. Okay, so let's go term by term again. All right, so first we have 1 over s minus 1. So this is a t shift, okay, or s shift, excuse me. And so this is the Laplace transform of e to the t. Okay. So essentially just the Laplace transform of 1 shifted by 1 by the exponential. All right, so next we have 1 over s squared. So we know this is the Laplace transform of t. Okay. All right, so that also comes from our table. Now this is the one that can be a little bit tricky because technically you can decompose this one more time. And so this 1 over s squared minus 1 is 1 over s plus 1 times s minus 1, right? And you can decompose that. Or if you wanted to, from the very beginning, you could just decompose s squared minus 1 to separate terms. But I did it this way just because this is kind of the new thing that we learned today. So I wanted to give you guys a little bit more practice with it. But this expression here, 1 over s squared minus 1, actually is in our Laplace table. It's just that we haven't used it up to this point. So this 1 over s squared minus 1, this is actually the Laplace transform of hyperbolic sine. So this is Laplace transform of sine h of t. Okay, so now we're finally ready to invert this, just because we've technically already inverted it, right? And so we have y of t is equal to e of t minus t plus hyperbolic sine of t. Right. All right, any questions on this example here? We kind of got everything? Okay, good. Yeah, so that's the process. I think that's our first time, kind of going beginning to end solving a differential equation with Laplace. And so when you're solving other differential equations, it's essentially this exact same process. It's just different spins, different types of partial fractions that you have to do. Okay. All right, so let's do another one. So let's do one with an oscillator this time. Okay. Okay, so let's consider the following initial value problem. So we have d squared y dt squared plus dy dt plus 9y is equal to 0. Okay. So luckily we have a homogeneous problem here. So the right-hand side is 0. And then for our initial conditions, we have y of 0 is equal to 0.16. Okay. So we're starting with an initial offset for our solution value, but its derivative, dy dt at t is equal to 0. We're going to assume that there's no velocity. Okay, so the derivative term is 0 at the start. Okay, and then just like the previous problem, we are interested in solving for the solution y of t, and we're going to do that using Laplace transforms. All right, so just like we did in the previous problem, we're going to follow our 3-step process. And so we're going to, take the Laplace transform of this equation, use algebra to solve for y of s, and then probably do partial fractions along the way. And then after partial fractions, we can invert it to y of t. Okay, so first we have step 1. Okay. Step 1 is take Laplace transform of the entire equation. Okay, so we're just going to take the Laplace transform of every term individually, right? So you have the Laplace transform of d squared y dt squared plus Laplace transform of dy dt plus Laplace transform of 9y is equal to Laplace transform of 0 is still 0. Okay, so I'm not going to write Laplace transform of 0. Okay. All right, so let's go ahead and evaluate all these Laplace transforms. All right, so first we have the Laplace transform of the second derivative, and so we've done this before. So this is s squared, big Y of s, minus s times y of 0 minus dy dt evaluated at t is equal to 0. Okay. Plus, we have this guy here. So Laplace transform of dy dt, this is just s times y of s minus our initial condition, y of 0. Okay. And then finally, we have the Laplace transform of y of 9 times y. So remember, 9 is just a constant here. So we can factor the 9 out in front because, Laplace transforms is a linear process. So we have 9 times y of s is equal to 0. Okay. Good. So next, let's go ahead and plug in our initial conditions. And so luckily, our initial derivative is just 0. And so we can just go ahead and just kind of wipe that term out right there. Okay. And then both locations where we have y of 0, we can go ahead and plug in our initial condition, which remember is 0.16. Okay, so we do that, we get s squared y of s minus 0.16 times s plus s big Y of s minus 0.16 plus 9 Y of s is equal to 0. Okay. Okay, good. All right, so let's go ahead and move on to step 2. So now that we have taken the Laplace transform of everything, we can go ahead and algebraically solve for Y of s. So step 2, algebraically solve for big Y of s. Okay, so this one's pretty simple. We're just going to take our two non-y terms. We're going to move it to the right-hand side. Okay, and then everything else, we're just going to factor out y of s from. So we have y of s multiplied by s squared plus s plus 9 is equal to 0.16 s plus 0.16. Okay. Good. All right, and then last step here, we're just going to divide both sides by that quadratic term. And so we have y of s is equal to, I'm going to go ahead and factor out 0.16 from both terms on the right. So we have 0.16 multiplied by s plus 1, all divided by s squared plus s plus 9. Okay, good. Step 3. Now that we have an expression for y of s, our solution in the Laplace domain, our last step here is just to take its inverse. Okay. Right, but first thing, we always ask ourselves, do we need to do any partial fractions? Okay. So I would say, most of the time you do have to do partial fractions just because you end up with something weird over there. But this is one of the rare cases where partial fractions actually doesn't really help you at all, right? So if you look at our denominator, right? Our denominator here is just simply s squared plus s plus 9. And so we have a quadratic function here. We can't really factor this into anything else, right? Okay. Right, and so there would be nothing to really decompose into, because if we do partial fraction, we end up with just one fraction to decompose, which is just simply the s squared plus s plus 9. So we're kind of stuck with this form right here. So we have to find a way to invert it. Right? So in this case, we don't need partial fractions, and so that is a welcome sight for sure. But that we're not necessarily out of the woods just yet. Okay, so we have to figure out what we can do with this denominator. Okay. Because if you look at our Laplace transform table, there's nothing in our table that looks like this. Right. So the question we're asking ourselves now is, how do we take that denominator and how do we get it into a form that we can take the inverse of more natural? Okay. Now, the big hint that you have here is that we do have a quadratic function, and most of the time when you have quadratic functions, right? Specifically, you have quadratic functions where there are no negative signs, right? So you have basically just terms added up everywhere. Okay. That's usually a good hint that you're looking at a sinusoidal solution. Right. That's usually a pretty good hint, because if you have quadratics in the denominator, there's no negative sign, so it can't be hyperbolic sine or cosine. You're probably looking at cosine or sine, okay? Because that's kind of the form that we look for. Okay? But it's not just any sine or cosine. It's going to be a sine or cosine with a shift. Right, so recall that whenever you have s plus something in the denominator, right, or you multiply something by e to the t, e to the at in the time domain, right, and you Laplace it to the Laplace domain, you end up with the shift in the s, right? And in fact, this is an entry that is given in our table as well. So this is the Laplace transform of e to the at multiplied by cosine omega t, e to the at multiplied by sine omega t. Okay. Okay, so all this is telling us is that, we do have to work on the denominator. We do have to do something here to make it inversible. But the thing that we're going to do is actually something that we did not, I don't think we did it last Thursday, but we did do it last Tuesday, which is complete the square in the denominator. Okay. So that's kind of my thought process when I kind of look at something like this. And so, the thing with Laplace is that, once you kind of start to see a lot of these and you do a lot of these for practice, you start to kind of see these patterns and you kind of know, just instinctually or just more easily say like, yeah, that's where I need to go. I need to get this into sine or cosine. I need to get this into a sine or cosine with a shift, right? And so this is kind of the thought process that I would go through in order to reach that conclusion. Because a lot of times when you read these kinds of examples in your textbook, they just kind of say, oh, we're just going to complete the square. Like it's the most obvious thing. And so, it's not the most obvious thing. You have to kind of do these a lot. And so, that's why I try, whenever possible, to kind of dump my thought process onto the page so that, it's there for you guys to kind of see that it's something like this. It's not as automatic as like a textbook may make it seem. There is a little bit of reasoning. There is a little bit of, process of elimination that kind of goes through. So that's kind of why I did that. Okay. So let's go ahead and do that. All right, so we have s squared plus s plus 9. So let's go ahead and let's try to complete that square. Okay. Okay, so if you remember our complete the square formula, basically, we're getting it into this form, right? So when you have, s plus a quantity squared, this is equal to s squared plus 2a plus a squared, okay? 2as, excuse me. And so the question is, if you have s squared plus s plus 9, what is the value of a in this square that we're going to complete, okay? Okay, so in our original expression here, the coefficient for this is 1, right? And so if we match that up with the second term here, right? So that 1 is equal to 2a. And so that means to complete the square, we are completing the square with an a value of 1/2, okay? Okay, so that means if a is 1/2, then we compute a squared. That means a squared is 1/2 squared, which is 1/4, okay? So that means in order to complete the square, we need to do s squared plus s plus 1/4, okay? Right? Because that's going to yield for us s plus 1/2 squared. Okay? But since we added 1/4 there, we need to subtract 1/4, okay, just so that we're all kind of even Steven. Okay. Right, and then we can't forget our 9. Okay, so we evaluate this. We can go ahead and complete this square. So this is s plus 1/2 quantity squared plus 9 minus 1/4. And so that is 8 3/4. 8 3/4 is 35 over 4. Okay. All right, so let's go ahead and plug this back into our y of s. So y of s is equal to 0.16 multiplied by s plus 1, all divided by s plus 1/2 quantity squared plus 35 over 4. Okay. Okay, good. All right, any questions on how we kind of got to this point here? Okay, all right, so let's keep going. All right, so we've done kind of most of the work here. So now it's just kind of playing with the form of this to get it to the form we need. Okay. Okay, so first thing we see from this is that, since we have an s plus 1/2 in the denominator, that means we are working with a shift of 1/2. Okay. Right. So that means, if we're gonna inverse Laplace this into a cosine term, that means we also need to have s plus 1/2 in the numerator as well. Okay. So for e to the at cosine omega t, need to have s plus 1/2 in numerator. Okay, so let's do that one first. Okay. So we have y of s is equal to 0.16. Okay. So luckily, we can see that 1 kind of splits into 1/2 plus 1/2. So we have 0.16 times s plus 1/2 plus 1/2. Okay. Over s plus 1/2 quantity squared plus 35 over 4. Okay. All right, so we can take one of these 1/2s and kind of just kind of boot it out, right? And so if we take that, we kind of separate this second 1/2 into its own fraction. We get big Y of s is equal to 0.16 multiplied by s plus 1/2 all over s plus 1/2 quantity squared plus 35 over 4. Okay. right? And then that 1/2 that we booted out in order to get this into the right form, that's going to be its own term. Right? So we have 1/2 multiplied by 0.16, that is 0.08, all divided by s plus 1/2 quantity squared plus 35/4. Okay. Okay, good. So we're basically there, right? And so, first term in this expression, we can see we can take its inverse because this is a shifted form of cosine omega t, right? Oh, let's note what omega is, right? So our omega here is going to be a little bit weird just because we don't have a term here that's easily, square rootable, right? So in this case, omega is equal to square root of whatever number is added right here. And so this is going to be square root of 35/4. Right? If you want it to be a little bit simplified, you're kind of a little bit kind of pedantic about this, technically you can take the square root of 4. And so this is square root of 35/2. Same thing, right? Personally, I like to have kind of the square root over the entire expression. I think it looks a little bit cleaner, but it's a kind of a personal preference. Okay. So with that, we can go ahead and take the Laplace inverse of this. Okay. So Laplace inverse of this is 0.16. That's a constant that just kind of comes out in front. E to the minus t/2, right? So there's our shift. So we have a shift of a 1/2. Okay. Multiplied by cosine of square root 35/4 times t. So you can see that, our shift plays a role here. Our shift became that e to the minus t/2. And then our omega here was square root of 35/4, which goes right into our cosine term. Okay, good. So that's our cosine. Our sine term also is right there, but we do have to kind of finagle this a little bit, right? Because remember, for sine, right? Right. So in order to inverse sine omega t, we need to have a constant term of omega in the numerator up there. Okay. So this one's a little bit more complicated because we're going to basically just do our multiply by 1 trick. Okay. So this becomes, right? So we need to have square root of 35/4 in the numerator here. Okay. S plus 1/2 quantity squared plus 35/4. Okay. 0.08. But since we're putting a square root of 35/4 in the numerator, that means we have to put a square root of 35/4 in the denominator, because we can't change the value of this expression here, but we can, manipulate the terms to get it into a slightly nicer form. Okay. All right. So unfortunately, we kind of end up with something that kind of just looks like a mess, but that happens sometimes with Laplace. Okay. So with that, we're able to inverse this, and so now we can inverse this. Okay. And unfortunately, it did not end up on the same line, but that is okay. So this is 0.08 divided by square root of 35/4 sine of square root of 35/4 times t. Okay. And there's our expression for y of t. Just a little bit lopsided because I was, poor planning on my part. Okay. So, as you kind of get more and more practice with these Laplace transforms, you'll see that, it's not so much, I think Laplace is not too difficult of a concept to understand. It's basically you're following the same 3-step process. But where Laplace, I think, gets really tricky is that you do have to have a really good grasp, a really good understanding of algebra in order to kind of do all these little tricks in order to kind of, manipulate these expressions to get them in the right form where you can take the inverse, right? Sometimes that involves doing partial fractions. Sometimes that involves completing the square. Sometimes that involves, a lot of, multiply by 1, adding 0 tricks, right? And so, a lot of these things you kind of just have to keep practicing it, and then you kind of start to kind of see these patterns. Okay? All right. Any questions on this? Yes.
Can you explain how you got 0.08 again?
Sure. So that 0.08, that was kind of born from this term right here. So, this is how we started. We started with 0.16 times s plus 1. And so first thing we said is that, we need to basically, for our cosine term, we need to have an identical shift in the numerator and the denominator. And so since in the denominator we had a shift of 1/2, that means we needed to have a shift of s plus 1/2 up top. And so first thing I did was I broke up that s plus 1 into s plus 1/2 plus 1/2. And so that extra 1/2 that kind of came out here, that kind of became the 0.08 because we have 1/2 multiplied by 0.16.
Okay.
Yeah. Yeah, good question. Any other questions on this example here? Okay, so if you look in the lecture notes, I have about 3 or 4 more examples for you to look at. So I would definitely recommend doing that. We could spend, weeks kind of just doing examples of these, and it would be endless. And so, I would definitely recommend looking at those as you practice. But for the last 5 minutes today, I kind of just want to put a bow on this section before we move on to step and impulse functions on Thursday. So let's talk about some of the advantages that you have when doing Laplace versus kind of the classical way of solving differential equations. Okay. All right. So for the first advantage is that you don't have to solve a homogeneous solution, right? So if you think back to our previous unit, right? So let's say that you have a second order ordinary differential equation with a non-homogeneous term. You kind of had to solve it in 2 steps. You solve the non-homogeneous solution first, or you solve the homogeneous solution first. You got the general solution, then you solve the non-homogeneous part. So there's kind of lots of different steps to involve in that, right? So the first advantage is that, no matter if you have a homogeneous problem or a non-homogeneous problem, your solution method is the same. Okay. And so in some sense, there's less procedural steps that you have to kind of memorize because, it's all just the same kind of process, right? So whether you have a homogeneous problem, the previous problem we just did was a homogeneous problem, or a non-homogeneous problem, like the first example we did, the process is exactly the same. Okay. All right, number 2. Right. So there's, when you're using Laplace, there's no sense of a general solution. And so there's no way to obtain that. The reason for that being that initial conditions are baked right into the solution procedure. Okay. Right. So there's no extra step that you have to do. So there's no general solution that you have to find, no arbitrary coefficients that you have to solve for using the initial conditions, right? So those are kind of accounted for right from the beginning. So you don't have to kind of, again, there's less procedural steps that you have to memorize. So it's all part of the same process. Okay. And then number 3, you know, we haven't gone over this yet, but this is kind of a preview of what we're gonna do on Thursday, is that 3 is that, you know, we can do, or we can solve problems with more, I would say, unique and more, I would say, practical, non-homogeneous terms. And specifically, you know, these kind of special non-homogeneous terms are specifically, you know, practical for engineering applications. And so I know, you know, on the one hand, the last 3 lectures have been a little bit rough just because, you know, it's just been pure math. We've kind of gotten away from the applications a little bit just because we kind of just had to learn how Laplaces work. But starting on Thursday, you know, we're going to get back into the engineering applications. Okay. So the two non-homogeneous terms that we're going to look at, one of them is called a step function. Right? So a step function is basically a function that is abruptly turned on, right? And you can also abruptly turn it off as well, right? So that's useful for situations where, you know, you have like a switch. So let's say you have a circuit with a switch that you can flip on and flip off, right? And so, you know, that's very useful for that. And so you can solve differential equations with a forcing function that looks like that, okay? And the other one that we're probably not going to get to until next week are impulse functions. So these are functions that occur over a very, very brief period of time. So they look just like this. So that's perfect for situations where, you know, maybe you have a hammer blow, right? You have an impact kind of situation, like we talked about in the mass spring damper. That's much more easy to model using Laplace, especially if you're going to have multiple impact scenarios, right? Not just. Okay. Any final questions before we wrap it up for today? Okay, all right, so that's all the time we have for today. So when we come back on Thursday, we'll start our discussion of step functions and we'll see how that forms with Laplace. So thank you guys for coming today. Hope you guys have a good rest of your day. Stay warm. It is really cold outside. I am like dying up here. And I'll see you guys on Thursday. Yeah.
For the traditional pathway, minor.
So there's a form for it online. So there's a form where you can kind of declare your minor. So basically it's I think it's called like a change of study plan form. And so the first time that you're declaring your minor, there's no fee. You just kind of fill the form, say I want to do a math minor. And so it's like, okay, you do a math minor. And then you just take the classes, then you graduate with that minor.
You know roughly kind of what classes that entails.
So there's different math minors. So if you're going to go for just the traditional math minor, that was actually very easy to do because you just kind of take the 3 additional, and then basically you just take 3 upper division math electives. So there's a list that you can find online for another math course that you can take for the math minor. The reason for that is, you know, for engineering, you already take the entire lower division series.
Yeah.
That's 150 A, B, 250 A, B, and so that's already, you know, 4 out of the 7 courses you have to take for the minor, and it's just 3 upper division electives.
Are those upper division electives usually theoretical?
I think they have a mix. So I think they have different electives for more theory and proof-based classes. And they have some which are more, they have a couple computational classes as well, where like you kind of develop computational algorithms and you kind of implement code. But yeah, yeah, but it's the math department, so they're going to skew more towards like, you know, like proofs and things like that, more so than applications.
Just appreciate it.
Yeah.